All right, so in this video, we're going to evaluate the integral of e to the negative x squared dx from negative infinity to positive infinity. So to start this out, let's call the answer to this integral I. And notice our variable of choice is x. What if instead our variable is y, so that we had e to the negative y squared dy? Will that change the answer to this integral? It turns out it wouldn't. Right? It's just like if we had something like this, right? You can verify that these two definite integrals are equal to each other. So it doesn't matter what we call our variable. The result will still be the same. Now, suppose that we were to multiply these two integrals together. Now, really, what we're doing here is we are multiplying two things that are equal to each other. They're both equal to I, so we're effectively doing I times I. So this is really just I squared. Now, another thing is we can re-express this product of integrals into a single double integral. Just like this. And notice we are multiplying two exponentials of the same base, so we can add the exponents. So what we get here is e to the power of negative x squared minus y squared. And also, in the exponent, we could factor out the negative, so we get the negative of x squared plus y squared. Just like that. Now, what we're going to do is we're actually going to change this to polar coordinates, right? We're going to convert x and y to r and theta. If you recall from polar coordinates, we know that x squared plus y squared is equal to r squared. And if you recall, dx dy is equal to r dr d theta. And so we're going to use these two facts to re-express our double integral into polar coordinates. We're going to replace the x squared plus y squared with r squared. We're going to replace the dx dy with r dr d theta. And if we do that, we will get something like this. But there's still one question that still remains unanswered. What do our bounds of integration become? Notice, when we're integrating with x and y, we integrate x from negative infinity to positive infinity, and we integrate y from negative infinity to positive infinity. What that means is we're integrating over the entire xy plane. And that's exactly what we want to do in polar coordinates. We want to make sure that we reach every point in polar coordinates. And to do that, when we're integrating with respect to r, all we do is we integrate from 0 to infinity. If you recall, r represents the distance from the origin. And so to reach every possible point in the coordinate plane, we need to integrate from a distance of 0 from the origin to a distance of infinity from the origin, right? That's essentially what we have to do. Okay, so then how do we integrate theta? Well, we need to make sure we reach every point in the coordinate plane, and the way we do that is we go in a full circle. We integrate from an angle of 0 to an angle of 2 pi radians. So just like that. So at this point, what we're going to do is we are going to evaluate this double integral. Starting with our first integral, I'll call this integral integral A. We're going to evaluate integral A up here. So how do you suppose we could start off evaluating this integral? Well, we could start out by doing a u substitution. If we set u equal to negative r squared, then this means that du is equal to negative 2r dr. Now, at this point, we know that we're going to be replacing the negative r squared with u. So then what are we going to replace the r dr with? Well, notice if we take our second equation and divide negative 2 to the other side, we get this. So as a result, we're going to replace the r dr with negative 1/2 du. So keeping that in mind, we're going to use that to re-express this integral in terms of u. But there's still one question that remains unanswered. What do our bounds of integration become? Now what we're going to do is we're going to use this equation to determine our new bounds of integration. If we look at our previous bounds of integration, notice that at r equals 0, if we plug that into this equation, we get u equals negative 0 squared. Therefore, u equals 0. And that's our first bound of integration, u equals 0. For our second bound of integration, notice that when r is essentially infinity, if we plug that into this equation, we essentially get u equals the negative of infinity squared. So u is essentially negative infinity. So that's what our second bound becomes. So this is our new integral in terms of u. Now, since negative 1/2 is a constant, we can pull it to the outside of the integral. And at this point, evaluating an integral like this one is pretty straightforward. We all know that the antiderivative of e to the u is e to the u. But before we do that, notice that one of our bounds is negative infinity. Whenever one of our bounds is at an infinity, we like to impose a limit on this. In other words, what we do is we say limit as some number b approaches, in this case, negative infinity. And what we do is we replace that bound with b. So something like this. Because this is really what it means for this bound to be at negative infinity. It's really a limit. So now we can evaluate this integral. Again, we all know that the antiderivative of e to the u is e to the u. So we get, and if we perform our substitutions into e to the u, we get, and we all know that e to the power of 0 is just 1. And now at this point, what we can do is we can evaluate this limit. Notice that as b approaches negative infinity, we essentially get e to the power of negative infinity, which is essentially 0. So really, this limit is equal to 0 minus 1. As a result, this is just positive 1/2. So this is what we get for integral a. So what we're going to do is we're actually going to move back up to the top and rewrite what we have here, but I'm going to replace what we have in red with just 1/2. And if we evaluate this integral, we're just going to get 1/2 times 2 pi minus 0, which means that I squared is just equal to pi. But if we take the square root of both sides, we know that the square and the square root cancel out, and we get a plus or minus. So I is equal to plus or minus the square root of pi, or I, better known as the integral from negative infinity to positive infinity of e to the negative x squared dx. So I'm going to replace I with the integral that we were trying to evaluate in the first place. So this integral is equal to plus or minus the square root of pi. But that's strange. How can a definite integral have two possible values? That seems odd. Well, it turns out that only one of these values is correct. It's either positive square root of pi or it's negative square root of pi. And if you think about it, our integrand, e to the negative x squared, is always positive for every x value. Since e to the negative x squared is greater than 0 for all x, that means that the integral from negative infinity to positive infinity of e to the negative x squared should be greater than 0. And as a result, we're left with no choice but to choose the positive square root of pi. Hence, we get that this integral is equal to the square root of pi. So, this is it. This would be the answer to this integral, the square root of pi.